So in this video, we're going to be learning about Newton's third law. We're skipping Newton's second law, but we will come back to it in not too long. So way back when, the Greeks, this is way back in history, the Greeks used to believe that in order for something to move, there had to be a force required. This kind of made sense in their everyday observations, right? Like if you want, say, a cart to roll down the street, you need a horse pulling it. You need some sort of force being applied to it for it to move. So it was logical based on what they observed, but is that actually true based on what we know so far? Well, the answer is definitely no, actually, not at all, because Newton's first law tells us that an object in motion, so something that's already moving, will stay in motion forever. It doesn't need a force to move it. In fact, it would need a force to stop it, to change its motion. So an object in motion will stay in motion forever if the net force is zero, if it doesn't feel any net forces. That's the idea of inertia. If you have a force, that actually is what you need to change the motion of the object, to slow it down or to speed it up. But it kind of makes sense why the Greeks believed that you need a force to keep things moving, because if in reality, right, there's always like friction forces that are slowing things down, and so you need a force to oppose that. Like if you have, here's your cart here. In reality, there's these, there's your cart. In reality, there's these friction forces backwards, and so you're going to need some sort of an applied force forward in order to have a net force of zero for the applied force and the friction force to balance each other out. So that's why the Greeks had believed that. But in reality, we know from Newton's first law that an object in motion will stay in motion forever. That is the first law. Newton noticed a few more things about forces, though, that were pretty profound. So what he noticed was that forces always came in pairs. And these two pairs of forces were always equal in size, so the same magnitude, but they had the opposite direction, even if these objects were accelerating. So if you take two spring scales here and you attach them and you pull on one of them, if this spring scale is reading 6 newtons, this one will be reading 6 newtons as well, but this one will be pulling this way and this one will be pulling that way. Exactly the same size of force, but in opposite directions. So Newton called these forces action-reaction pairs. And he wrote his third law, which is the idea that for every action force, so every time you pull on something, there's an equal and opposite reaction force backwards in the opposite direction. Now, one thing to watch out for is that those action-reaction forces are not on the same object. So the idea of Newton's third law is that if you push on your friend, then your friend is pushing back on you with the same force. So those are on two different objects, right? You push on your friend, that's the force on your friend. You feel a force back from your friend on you, you're a different object from your friend, right? So these action-reaction pairs are always on different objects. We're going to do a whole bunch of examples to try to make sense of this. So the simplest situation, we've got Alex, this is Alex here, and Lewis. And Alex pushes on Lewis with a force of 5 newtons. So that's the force of Alex on Lewis. What will be the reaction force? Well, it'll simply be the force backwards that Lewis pushes on Alex. So the force of Lewis on Alex. You may have run into this if you've ever tried to push someone who is bigger than you. You push on them with a force of 5 newtons, and you will feel the 5 newton force backwards from them. And if they're a lot bigger than you, you'll be the one that does more acceleration. In other words, you'll fall over. If you've ever seen a really small person try and tackle a big person, usually the small person is the one that bounces back. But both people are actually feeling the same force. So the force that you exert, or that Alex here exerts on Lewis, is going to be the same as the force that Lewis exerts on Alex. So the reaction force is the force Lewis exerts backwards on Alex. And it's not that like Lewis turns around and then intentionally pushes Alex, just the motion of Alex pushing on Lewis puts a force in Alex's hand that is backwards on Alex and will cause him to also feel a backwards force. Let's say you push on a wall with a force of 20 newtons. What is the reaction force here? Well, it feels a little bit weirder with a wall, but it's actually exactly the same idea. The wall is pushing backwards on you. So you feel a force from the wall of 20 newtons as well. So that's the reaction force, and that's why you might move away from the wall. So let's say you're standing on a skateboard, so you're nice and easily to move. You push on a wall with 20 newtons, you'll notice you start rolling away from the wall, right? That's because the wall pushed on you with 20 newtons as well. You applied a force of 20 newtons to the wall pushes back on you with 20 newtons. All right, some slightly trickier examples. Let's say you're standing on the ground, so here's you on the ground, and we know you feel a couple of forces, right? You feel the force of gravity down, and you feel a normal force up here. Let's look at that normal force first. What is the action-reaction pair to that normal force? We have to think about what the normal force is. It's a force from the floor pushing up on you, and it's the reason why you don't fall through the floor. The action-reaction pair of the normal force is not gravity. I'm just going to write that in here so we remember. It's not gravity. The reason why the reaction to the normal force could not be gravity is for a few reasons. One is that gravity is on the same object as the normal force, right? You feel the normal force, you feel gravity. Action-reaction pairs are always on two different objects. So like Alex pushes on Lewis, Lewis pushes back on Alex, right? Those are on two different people. So it could not possibly be gravity. This gets a bit confusing, right? Because the normal force and gravity are in the opposite direction. So we go, oh, opposite forces must be action-reaction pairs, but they're not here. They just happen to be in the opposite direction here. If you were on a slope, the normal force on you, here's you, would be this way. Gravity would be down. Right here, they wouldn't be in opposite directions, right? So they're not always in opposite directions, and they're not always even equal. If you were accelerating upwards or accelerating downwards, they would not be equal. So lots of reasons why gravity could not possibly be the action-reaction pair. I'll just erase some of this stuff here. All right. What is the reaction-reaction pair then? So the normal force is the force of the floor pushing up on you. So the reaction pair must be you pushed down on the floor. With a 500 Newton force downward. And then let's look at gravity. So same situation, you feel gravity when you're standing on the floor, and maybe you feel a force of gravity of 500 newtons, and that's a force down. So the reaction force must be an upwards force. It's always in the opposite direction. It must be a magnitude of 500 newtons. But what is it on? What we have to think about here is what actually caused the gravity? What object was pulling on you when you felt this force of gravity down? And that's the Earth, right? The Earth caused gravity. So gravity, let's just write down what gravity is. So gravity is the Earth pulling down on you. That means the action-reaction pair to that must be you pulling up on the Earth. So the reaction force is you pull up on the Earth. With 500 newtons. And that's in the upwards direction. That probably feels weird. So right now at this very moment, you are currently pulling upwards on the Earth with 500 newtons. But the Earth isn't really going anywhere, right? It's not really moving towards you because you're pulling on it with 500 newtons. Why is that the case? Well, that's because the Earth is so much more massive than you. So when you pull on the Earth, it's so massive that even though you pull with this decent-sized force of 500 newtons on the Earth, if you just exert 500 newtons on an extremely massive object, which is the Earth, it's not going to accelerate very much. It's not going to really budge from that force. Right, so just some helpful things. Let's see if you remember. What is true about action-reaction pairs? Are they always on the same free body diagram? Always on different free body diagrams? Always equal in magnitude? Do they always point in the same direction? Think about it for a second. Which of these is true? They always have to be on different objects, so they're always going to be on different free body diagrams, and they're always equal in magnitude, but they don't point in the same direction, they will always point in opposite direction. All right, let's do a few more examples. So let's say this is Christian, this is Hannah. So Christian here, Hannah. And Hannah decides to push Christian. I put them on skateboards so that you can see what happens a little bit better in this situation. So during the push, of course, Hannah's exerting a force on Christian here. So this is the force of Hannah on Christian. So I'll use the subscripts HC, meaning Hannah on Christian. So Hannah will feel an action-reaction force from that, which is exactly the same magnitude. And that's going to be the force of Christian on Hannah in the opposite direction. So what will happen to them? Well, both of them feel a normal force from the ground, right? And both of them feel gravity. But these will balance, their gravity and their normal forces will balance out. And so if I look at just a picture of Hannah here, so just zoom in on Hannah's free body diagram, then what you'll notice is that the net force on Hannah is going to be to the right. So the net force on Hannah, so this is on Hannah, is going to be to the right. That means that she's going to accelerate to the right. So Hannah will accelerate in the direction of that net force. So the direction of her net force, which is right. If we look at just the free body diagram of Christian, it's the same idea here. We'd feel a force of gravity down and a normal force up, right? Fn and Fg here. But those forces will cancel each other out. Those will be balanced. So the net force on Christian will just be this force to the left from Hannah. So the net force on Christian is going to be to the left. So therefore, he's going to accelerate left. Because we always accelerate in the same direction as our net force. All right. Let's do a more childish example. I've been reading lots of children's books these days. So you may have read Yertle the Turtle. If you haven't, highly recommended. Great book. But it's a story of King Yertle, who believes that if he is taller and can see more, then he'll be king of all he can see. And so he forces turtles like Mac to make a stack underneath him so that he can be taller and see further. It doesn't end well for Yertle, but you'll have to read the book to know the ending. But it starts out with a stack that's just 2 turtles high. At the very beginning, Yertle just recruits this poor turtle named Mac to stand there while he sits on Mac's back and looks at all he can see. So in this moment, let's do a free body diagram of Yertle. So we'll go on this free body diagram. So here's Yertle, the turtle. My turtle. Doesn't really look like a turtle, but there we go. Yertle will feel just a few forces, right? He feels a force of gravity. That's his own gravity. Right, so just based on his own mass. So his mass is 12 kilograms times 9.8. That would be that force of gravity there. Then he feels a normal force upwards, and that's the force from Mac. So it's a normal force, but it's specifically a normal force from Mac. So maybe I'll call it Fm. Y. So that's Mac's force on Yertle, force of Mac on Yertle. It's a normal force, but specifically a normal force from Mac. What is the action-reaction pair to that normal force from Mac on Yertle? Well, if Mac is pushing upwards on Yertle, then Yertle must be pushing downwards on Mac. So the reaction is Yertle pushes down on Mac. This is why it's hard on Mac's back. And so we would give the notation to that force. It would be an F-Y-M, or force of Yertle on Mac there. Let's look at the free body diagram of Mac then. So here's Mac. There we go. He feels his own gravity. That would be the 10 kilograms that he weighs times 9.8. And he feels that force downwards from Yertle. That's what's painful for the poor guy. That's the force of Yertle on Mac here. And so Mac will need to feel a normal force from the ground so that he doesn't fall through the ground. And that normal force is going to have to balance out two forces, both the force of Yertle on Mac and Mac's own gravitational force. So if I added up all the forces in the y direction here, this normal force plus these two negative forces, Fg and Fym here, all have to add up to 0 so that Mac is not accelerating. All right, a few more examples here. Let's say you have a cat sleeping on the ground. What's the action-reaction pair to the force of gravity on the cat? We've done this before. See if you can think of it. What would it be? There's a cat sleeping on the ground. The action-reaction pair to the force of gravity on the cat. Is it the force of the ground pushing up on the cat? That would be wrong, right? No, it's not that. It would be, the gravity is actually the earth pulling down on the cat. So the action-reaction pair to that must be the cat pulling up on the earth. So the action-reaction pair to gravity is a force that the earth feels from the cat pulling up on the earth. So no wonder the cat's tired. It's spending its time pulling up on the earth. All right, here's one more example. So let's say you have a large truck, it's a red truck here, is pushing on a small green car. And the truck causes the car to move at constant speed. We're going to call FTC the force of the truck on the car, and FCT the force of the car on the truck. So I'd like you to take a second to think about it. These are magnitudes, so the magnitude sign means we're looking at just how big the force is, not what direction it is. Those forces, of course, will be in different directions. But you're just looking at which one's bigger. Is the force of the truck on the car bigger? That would be V here. Or is the force of the car on the truck bigger? Or are the two forces equal? Take a second to think about it. The answer is C. Hopefully you were thinking C. So the force that the truck exerts on the car is going to be exactly the same size as the force that the car exerts back on the truck. Now what if we have the same scenario, but now the car accelerates? Now will the force of the car pushing back on the truck be bigger than the force the truck exerts on the car? Or will the force the truck exerts on the car be bigger than the force of the car on the truck, or will they still be equal? Think about it for a sec. Hopefully you were thinking C, and that's because Newton's third law applies even when an object is accelerating. So Newton's first law, that objects in motion will stay in motion forever, only applies if there's no net force in the object and if the object is not accelerating. But Newton's third law applies all the time, whether objects are accelerating or not, whether they have the same mass or not. Newton's third law is still true. So let's just write this down. So Newton's third law is true even when your objects are accelerating. Or when the objects have different masses. Which is also the case here too. So Newton's third law is always true. For every action force, there's always an opposite reaction force back on you. So if the truck is pushing on the car with, say, 1,000 newtons, the car is pushing backwards on the truck with 1,000 newtons as well. Those forces are equal even if the car is speeding up while the truck is pushing on it. That probably feels weird because you might think, well, if these forces are equal, then how could the car accelerate? Like, it sounds like all the forces are balanced. But the thing is, the forces on the car are not balanced, and the forces on the truck are not necessarily balanced either, and that's why it's able to accelerate. It's just that the forces between the car and the truck, those are equal to each other. It's not that all the forces on the car balance out. So the force of the truck on the car appears on a free body diagram of the car. If I draw the car here, it would feel the force from the truck. It would feel it's a normal force, right? It would feel its own gravity. It might feel a small like friction force or something backwards of some kind, maybe. But clearly the forces here are not balanced on the car. This force from the truck on the car is much, much bigger than any sort of frictional resistance forces that the car feels. So the car will accelerate forwards because the net force is definitely in the forwards direction here. Notice the force from the car and the truck does not show up on the free body diagram of the car because that's a force that the car is exerting on its surroundings, not an external force that the car feels. The force that the car exerts on the truck has to show up on the free body diagram of the truck, not the car. So if I draw the truck here, it would feel a backwards force from the car. That's the force of the car on the truck. And that force will be exactly the same size as the force from the truck on the car that we drew in this free body diagram. And of course, the truck will feel a normal force, and it'll feel a gravitational force. And the truck will also feel a very large force forwards here. This force we're going to talk about later when we get into friction. It's actually also a frictional force. It's a static friction force that's going to cause that truck to accelerate forwards. We'll talk a lot more about that later. But that force will be bigger than the force that the truck feels back on the car. And that's why the truck is also able to accelerate forwards, because this force that's pulling the truck forward is bigger than the force that the truck feels from the car pushing it backwards. But notice, this force here, your force from the truck on the car, never cancels out the force from the force from the car on the truck never cancels out the force from the truck on the car because they're on two different free body diagrams. So some takeaways. Newton's third law always applies, even if your objects have different masses, even if the objects are accelerating. And Newton's third law, the action-reaction pairs are always on different free body diagrams or different objects.